Okay, working at washer method today with volumes of revolution. We have worked so far with finding volumes after taking a flat region and revolving it around an axis. We have used the disk method, and after revolving a region, we have bookshelved disks from left to right, integrated with a DX, and found volumes. We've also revolved around a vertical axis or line. We've stacked pancakes from low to high and integrated with a dy in order to find volume. So today, a little different. We are working with a shape with a hole in the middle called a washer. So this is what a washer looks like with tools, and notice the hole in the middle. So we've got to figure out, after we rotate a region over an axis, we're going to end up with a hole in the middle. We've got to figure out how to deal with this circumstance and how to find the area of each slice which has a hole in the middle. So pay attention, please.
I say pay attention, boy. Look at me when I'm talking to you, son. Look, sister, is any of this filtering through that little blue bonnet of yours? Pay attention, son. Look at me when I'm talking to you. Pay attention to me, boy. I'm not just talking to hear my head roar.
Okay, so let's review, first of all, something you learned in the olden days back in your geometry class. That is how to deal with finding the area of a circle that's got a hole in the middle. So we got to find the area of this shaded region. As we see, the outer is a circle, the inner is a circle, and then this shaded region is that region resting between the large and the small circle. So in order to do this, we've got to figure out the radius of first the larger circle, which we denote with a big R, and then the smaller circle, which we will denote with a little r. And we want to find the area of this game using the formula. I know pi r squared finds the area of one circle. We've got a scenario here. We've got to go the area of the big circle minus the area of the little circle. Picturing this as taking the big circle and drawing it on a sheet of paper and actually cutting out or subtracting that small circle. What you'll have left over is the area of that dotted shaded region. So just to give you an example here, if we assign radii of length 9 for the big circle and 4 for the small circle, we're going to go pi big R squared minus pi little r squared, getting pi times quantity 9 squared minus 4 squared, resulting in pi times 81 minus 16 for a final answer of 65 pi units squared. That's how we would find the area of a circular region with a circular hole in the middle. So let's take that and apply it to example 1 on our washer worksheet, where f of x is the curve root x plus 2, and g of x is like y equals 2. G of x equals to a horizontal line going through the y-axis at 2. X equals 4 is the vertical line going through the x-axis at 4. Our instructions are to rotate this enclosed region after we graph it around the x-axis and then find the volume. So the graph is going to be such that when we rotate it around the x-axis, there will be this void in the middle. Let's take a look at the graph. First is the graph of root x plus 2. It's just our parent function of root x translated up 2 units. You guys have been down that road. This is g of x equals 2, again the horizontal line piercing through the y-axis at y equals 2. And then the third equation, just this simple vertical x equals 4. You see the trapped region here that the 3 curves enclose. Now notice this region is floating above the x-axis. So when we rotate this, we'll see clearly this void we're going to rotate around the x-axis. So this void, semi-interesting here, and a little strategy for drawing this washer. I've called this the 5-dot method. I think that's what I called it. So the note here in yellow is saying, hey, to draw a sample washer, use the 5-dot scheme. What exactly does that mean? That just means choose a location within the region somewhere and plot these 5 dots. Check it. Dot 1, dead above 2, dead above 3, dead below 4, dead below 5. That's the 5-dot method. This is a nice technique in order to see these washers. So there's the small circle and there's the large circle. And remember, these washers are going to change size as I bookshelf these washers from left to right, just as our discs changed sizes. So we're going to move forward here and see how to attack. You know, you're integrating, you guys can see already, you're integrating between 0 and 4, and you're finding the area of each of these washers, and you already know how to find the area of such a washer. We looked at that in the previous screen. So again, the big circle has a radius, and the little circle has a little r radius. Maybe you can see already from the drawing what will be the value of that big radius and what will be the value of that little radius. Let's move forward. So we're bookshelving these washers from left to right. So we are integrating from 0 to 4, pi big R squared minus pi little r squared dx. The big R is equal to root x plus 2, root x plus 2, and the little r is equal to 2. If you're looking at your picture here, you're seeing that big R is equal to root x plus 2. We're going over the x-axis, so it would be root x plus 2 minus 0, in fact. And little r is always going to be 2, no matter which washer I'm talking about on the trip from 0 to 4. That little red radius is always going to be equal to 2. That makes sense to me. Hope you guys are seeing that. So, again, let me catch us up. We've got the volume is going to be equal to the integral from 0 to 4, pi big R squared minus pi little r squared. We've got our big R and our little r. And we're going to factor out the pi, integrate from 0 to 4, root x plus 2 squared minus 2 squared. Some of you perhaps are tempted to try to simplify that and link those two radii together. That's a common error that a lot of calculus students make. Please square each radius individually. Don't combine them and square it once. You must square each of these radii individually. So, root x plus 2 squared, I got to work a little first outside, inside, last here. Take a look. Root x plus 2 times root x plus 2. I multiply the first in each quantity. Root x times root x is going to give me that x. I multiply the outside and inside. This is going to be plus 2 root x plus 2 root x. That's going to yield 4 root x. And then last is just going to be that 2 times 2, which is going to kick out a plus 4. Now, why do I have that minus 4? Don't forget, you still, after squaring, have to subtract that caboose, that minus 2 squared. So I'm subtracting 4. I see that things simplify a little. But as I take and simplify this, I see toward the end of my integral, I've got a plus 4 minus 4. That's history. So I'm really just integrating the first and second terms. Well, integrating x gives me add 1 to the exponent, divide by the new exponent, x squared over 2. Plus, if I visualize 4 root x as 4x to the 1/2 power, it can help me realize adding 1 to the exponent, dividing by the new exponent, gets me 4x to the 3/2 over 3/2. Evaluating that from 0 to 4. Well, when I put a 4 in for x, I'm now using FTC1, plugging in the upper limit for x. I've got 4 squared, which is 16. Then 16 divided by 2 gives me that 8. Now I'm plugging in a 4 for the second x. 4 raised to the 3/2 power. Think of it as the square root of 4, 2 cubed. 2 cubed is 8. 8 times 4 is 32. Then I'm multiplying that by the reciprocal of 3/2, which is 2/3. Okay, so the math shown here gets you 64 over 3. Continuing, remember you have to subtract when you plug a 0 in for x. And simplifying your final answer gives you a volume of 88 over 3 pi units cubed. So, pretty impressive and powerful that you're actually able to figure out the volume of this region after it's rotated over the x-axis, and the region's got a hole in the middle of it. Pretty fantastic and powerful in calculus that you're actually able to do this. And when the dust clears, arrive at your final answer, 88 over 3 pi units cubed, finding the volume of a picture that looks a little bit like this. If you can get visual, like the song says, and picture each one of these washers bookshelved from left to right. Of course, you're going to run into scenarios just as you did with the disk method, where you will be revolving a region around the y-axis or something vertical. And the same story is going to occur. You just have to make sure your limits of integration are in terms of y, your integrand is written in terms of y, and you are integrating with a dy. So we've been through 2 different methods of volumes determined by revolving a region around a specified axis or line. We have but one volume strategy to attack upcoming before we are able to put some closure in on these volume challenges in calculus class. So take a look, work on the problems for some practice, and we'll see you soon. Volumes of Revolution, the washer method. Enjoy. Over and out.